let's give it like this. Okay, good. Good morning, everyone. So, let's start. So last time we were left with dark energy, so we were studying quintessence models. And we've seen that basically quintessence models are characterized by an ideal fluid. Okay, so we think at dark energy as an ideal fluid, and that's meant to basically avoid all the complications and conflict with particle physics that arise when you deal with the cosmological constant, right? Cosmological constant, we have two problems, fine-tuning problem. Why is it so crazy small but not zero? And why its value is such that exactly today, the value of dark energy and matter, the density of matter and dark energy are very similar, okay? So we decided, okay, let's set lambda equal to 0, so that's not part of the theory. So general relativity is not as general as it could be, but it's more restricted because of this case, okay? Because of this imposition. So we are dealing with a simpler theory of gravity, if you wish, but then we need to introduce dark energy, which is characterized by an equation of state, okay? So it's a field, it's a kind of field that characterizes our matter, our fluid, and is characterized by an effective equation of state. Equation of state, which is defined, as usual, as the ratio between the pressure and the density. Okay, that's the equation of state. That is a function in this case, because we have seen that it's not a constant parameter, as it is for matter or radiation, 1/3 of 0, well, 0 or 1/3, 0 is for matter, 1/3 is for radiation, so it's not a parameter, but it's a function of time, because we have seen that dark energy is being a dynamical field, can evolve as a function of time, given certain initial conditions. Because we have seen that such a model is just a fluid, so it's the description of a fluid, which is fully given by the Klein-Gordon equation. Okay, Klein-Gordon equation, I recall you, it's so Klein-Gordon equation, we have the phi dot plus 3h, phi dot plus the derivative of the potential with respect to the value of the field phi, okay? And we've seen it's an oscillation, it's a damped oscillator, where the damping term is given by h, so the fact that the universe is expanding introduces a damping in our oscillations, which is non-zero, and this characterizes the evolution, the dynamics of dark energy together with the other equation, which was Friedman. Right? That characterizes H. So these two guys have to be solved simultaneously. Giving an H, we have the behavior of dark energy, and giving a behavior of dark energy, we have the evolution of H. Okay, so the two have to be solved simultaneously, because you know that basically this guy depends on the matter content, radiation content. We put big M as this background that we intend to be matter or radiation, or the two together, and then we have omega associated to the field. Okay, and in general we have also the one associated to the curvature. But as we said, we are taking flat cosmology here, so the curvature is equal to 0. So you see that this guy is going to give phi is entering here, and therefore influence H, which influences these ones, and so on and so forth. Okay, it's a set to be solved simultaneously. So then we study a little bit the Klein-Gordon equation, and we realize the fact that it's so generic that can kind of, it describes fluids in general. So it could be matter, it could be radiation, when we have the oscillations, right, around the 0, the bottom of the potential. It could be slow rolling, and therefore we have our dark energy. That's what we know. That's what we need. We've seen what is the meaning of the slow rolling conditions. And then Could be, for example, even the cosmological constant. If we have the potential, we have seen, if the potential is such that the minimum is not as zero, and the field is not evolving, is static, meaning is sitting at the bottom of the potential without fluctuating, without doing anything, that's the cosmological constant, identified as a fluid. Okay? And you see already here, it is, if you wish, a little bit more fundamental problem with respect to what we've seen in the previous lecture. This is again fine tuning, because it's a field that in principle can do a lot of stuff, but no, it's precisely sitting statically at the bottom of the potential. Okay? So you see that it's way too specific, the cosmological constant behavior. That's why we went for dark energy. What is the problem here with this prescription? There is this V, right? V is given. V, the potential, characterizes the specific behaviors of a given model. You change V, you have a sort of dark energy, you use another potential, you have a different behavior for dark energy. Okay? Therefore, we have a variety of different potential you can play with, and you get different results. Okay? So what's the trick now? That since this guy is so generic, of course, we're not going to go through each of them and see what they're going to do, which kind of universe we get, and so on and so forth. As I said, we are going to, through the study of the phase space, okay? Because you see, this is given. So it's fixed, it's not a variable of our equations that we need to solve. The variables are, so the degrees of freedoms, are basically given by phi dot and phi. These are the two variables that characterizes our system. And as I said, these two variables define a phase space. A phase space that I already described during the past lecture. So you have like phi and phi dot, and then you're going to have solutions that are going across this phase space. Then during the past lectures, I already told you what is the power of the phase space, because different, already by studying, by knowing that we are dealing with such a system, we know, for example, that the solution cannot cross. Because otherwise, we might have given the same initial conditions to different paths. And that's not possible because this is a fully deterministic system. Okay? For example, or if we want to have the slow rolling condition for our field to be satisfied, we cannot have something like that, something very steep, because then it would mean that the values of the kinetic term will become extremely large, which means that we're going to break the slow rolling conditions. That's not what we need. Okay? So you see, just by simple consideration of this sort, we can constrain already the properties of our solutions without even solving them. So we are not going to solve individual solutions, because then, specific solutions, because then we would need to characterize this guy here, plus the other issues, the other issue, which is not minor for a blackboard, is that this guy can be solved numerically only. So there is not an analytical prescription, not even with simple potentials. Okay? So what we are going to do is to characterize the phase space position, and in doing that, we are going to introduce two new variables, x1 and x2, for convenience. So this is just for convenience. And we are going to characterize the potential with respect to two parameters. Lambda, which tells you what is the steepness of the potential, if you wish, and big gamma, which is going to tell you the curvature of the potential. So how its given profile, what is the curvature of its profile. Okay? And this depends on V. So these two functions are just lambda of a certain potential and gamma of a certain potential. You change the potential, you change the different gamma. So the trick now is that we are going to study the solution given a certain lambda and a certain gamma, whatever is the potential which is hidden in them. Okay? That's a nice trick, because now we can be very, very generic. Because then you have the whatever potential you want, the whatever potential you have, and you can see what's happening once you get a certain gamma, okay? So if you know what is the behavior with respect to lambda and gamma, you can characterize all the other potentials, all potentials you want, okay? Good, this is extremely powerful because this is going to tell us what's going to happen to our dark energy model, but we are losing, since our variable are phi dot and phi, we are losing track of time, okay? So we will know how the solutions are going around across our phase space, but we will not know, if you wish, at which speed. So we will not know at what time we are going to be there. But we will know in which direction we are to moving and where the solutions are going to behave in the phase space. Okay, so we have a full characterization of the behavior of our dark energy field and the universe in general, because we are going to study the phase space considering a matter source, and with matter I intend radiation or matter, dark matter, the baryons and dark matter, okay? So this would be the big M, where I don't make this distinction between radiation and the real matter. And we will be able to understand if we can have a model, a cosmological model, that first gives us a radiation domination epoch, then matter domination, and then dark energy, okay? In doing that, we need to study specific locations in the phase space that characterizes the different solutions. And they have to be characterized in terms of stability points. We already talked about that, because we can have, for example, a point which is stable. That's a critical point. We're going to quantify where these locations are, and they can be stable, meaning the solutions are going to end up there. And once they are there, they stay up. The universe, if we find a solution where is matter, for example, is characterized by a critical point and is a stable solution, we end up there and we stay in a matter-dominated epoch. We cannot escape into an accelerated phase, for example, okay? Or we can have unstable points where if we have an initial condition which is sitting exactly in that location and is a little bit perturbed, the solution will go away. We'll move away from that point. Or we can have saddle points in which we have sort of stability in one direction, but instability with respect to another direction. This would mean that if I, for example, have an initial condition sitting here, I would be attracted in this, so the system would go in this direction. Oops, let's took an arrow, it would be up. If it's attracted there, if, let's say, the impact parameter for the trajectory is going to be on this side, then, since the system is unstable, the system will do like that, okay? Will not stay there. Will stay there for a little, and then it would go away. So this is something important, because we want this sort of metastable, these partially stable points, in which for example, we start from the radiation, we want our system to transition to a matter domination epoch, we don't want it to be there forever. Then at a certain point, it must be free to go somewhere else, okay? Another thing that we are going to see is that the critical points are kind of fixed if this guy is constant. If lambda is constant, we are going to see which potential is giving you lambda constant. But if lambda is constant, then the critical points are fixed. And their stability is given. If a point is stable, it's stable. If it's unstable, unstable. If it's a saddle, it's a saddle. Okay? But if lambda is evolving, the nature of those critical points can change as a function of time. Okay? Therefore, you can have a point which, for example, is matter dominated as a stable point. Boom, you arrive there and you stay. Lambda is changes as a function of time, becomes a saddle point, and the solution can move away. Okay? So there are all these sort of behaviors that we are going to look now. Okay? So let's get started. And let's study the phase space in detail and find these magic critical points and see what the solutions are going to do. Okay? So we start with the Friedman equation that I call Friedman equation 2. So that's Friedman equation 2 that tells you how H is evolving. So this will be the second equation of our coupled system. That's equal to 8 pi g over 3c squared. Then we have rho meta c squared plus the contribution of dark energy. So you see we are going to have a universe which is populated by a matter content, again radiation or proper matter, plus the density of dark energy. Density of dark energy which can be characterized with respect to phi dot and the potential, right? Remember? So for example, the equation of state is equal to 1/2 phi dot minus V divided 1/2 phi dot plus V. And by definition of this guy, this is the pressure term and this is the density. Okay, if we keep C, the factor, if we keep the speed of light non equal to 1, then here we have a C to the power of 2. Okay, so that's this would be the density that we have. So rho C squared would be equal to 1/2 phi dot square. Did I put the square? No. Square in square. Phi dot square plus the potential. Okay, this will be our rho field C squared. Now for convenience, I'm going to set the speed of light equal to 1, and I'm going to call this very annoying factor, 8 pi g, I'm going to call it k. It's not the curvature, okay? It's not the curvature. Curvature is equal to 0, so that's something that we forget about, okay? So k is just the number. If we do that, then you see we have rho m here. We can divide this expression with respect to h squared. So I basically bring h to the power of 2 on the other side. And basically these terms with the h squared and rho m gives you omega m. Therefore we have our omega meta, which again is defined as k squared rho m, big M, rho m over 3 h squared. You see I have rho m here, I plug it to here. Okay, I just do that. That's equal to 1 minus k squared phi dot square over 6 h to the power of 2 minus k squared v, which is a function of the potential, 3 h squared. And then what do we do for convenience? Well, we define this guy x1 and this guy x2. Therefore, by definition, this is 1 minus x1 squared minus x2 squared. Yeah?
Ig should be k squared.
Sorry?
Shouldn't Ig be k squared? Or that should be k?
Ah, sorry. Squared. Thanks. Yeah?
Is the radiation needed?
What, sorry?
Radiation.
As I said, when I say rho m can be or radiation or, so rho big M, you can intend it as rho radiation or rho matter. So we are in a phase, so we are describing a universe which is where one of these two species is negligible. But when you see big M is one of the two. Okay? And I do that because if I wouldn't do that, the phase space would not be two-dimensional but three-dimensional. And therefore, the blackboard is going to become a mess, and I'm going to introduce the third dimension at the end. So we're going to study simpler cases where we have the domination of one with two species with respect to the other. This doesn't mean that they are dominating with respect to phi. Okay? They can also be equal and so on and so forth, but they are dominating one with respect to each other. Afterward, we are going to be more general. Okay? Otherwise, it's becoming a mess too fast. Therefore, we have x1, which is defined as k phi dot over square root of 6h. And then we have x2, which is k, defined as k square root of the potential divided square root of 3 of h. Now look at this expression. What we have for free is omega field, because we are assuming the universe to be flat, and therefore we know that omega m plus omega phi is equal to 1. Therefore this guy is actually minus, because there is this minus omega phi. Just for flatness, remember, flat. Omega m plus omega phi is equal to 1. Okay? Bring omega phi on the other side, we have 1. Omega m equal to 1 minus omega phi, which is exactly this expression. Therefore, what we get for free, omega phi, well, again, by definition, is the very same expression that we have here, now with phi for the density, over 3h to the power of 2, and that's equal to x1 squared plus x2 squared. Okay? With the plus, the minus is because it's 1 minus omega phi. Okay? Good. So, what is telling us, if we go back to these two guys, that x1 is related to phi dot, so the kinetic term, whereas x2 is related to the potential. Okay, so they give us these two information. Okay, now that we have that, we can play with the equation of state parameter, or function in this case, which is going to tell us if we are in an accelerated phase or not. Therefore, we have our equation of state parameter for the field, which is, again, the relation between P and rho. You don't find the C squared because we set C equal to 1. And then if we plug in the definition for dark energy, which is what I wrote up there, so for an ideal fluid, we have the kinetic term divided 2 minus the potential divided 1/2 phi dot square plus the potential. Okay? Now what we are doing, what's the game here? To transform this thing in terms of x1 and x2. That it's easily done, because we have phi dot square as a function of x1, and we have the potential v that we have here as a function of x2. So I just use these two expressions and I plug them into here and here. What we get is x1 squared minus x2 squared divided x1 squared plus x2 squared. Oh, that's nice, because you see, these are the key ingredients, and they're all described by x1 and x2. So whenever we find x1 and x2, we know what is the omega m, omega phi, and the equation of state of our field. We don't need it, okay? So you see here the power and the simplification that we get by introducing these two new parameters here. And now we have to be careful, because like in previous in cosmology, typically one was just studying matter-dominated epoch, radiation-dominated epoch, and so on and so forth. Now we can have values of phi that can be non-negligible, and therefore we might have radiation and the value of the field, which are similar, and the same goes for the matter domination. Therefore, we need to take care when we are dealing with the acceleration phase in this very generic picture, because what is given for real the acceleration of the universe is not the equation of state of one single species, but of the combination of all of them. Okay? Therefore, we need to deal with the effective equation of state of the universe, okay, given all its ingredients. And again, how do we define it? Well, again, it's going to be the pressure, this time total, so the pressure given by all its constituents, and the density total, again, all constituents of the universe. So what we do, well, this is just a summatory of all the components with respect to the pressure, given rho total. Rho total, which is what? We are assuming a flat cosmology. And therefore, the total density of the universe is the critical density. Rho equal to rho critical is the condition for flat cosmology. We can change this total for rho critical. Then what can we do? Well, we have our equation of state that is related pressure to the density. Therefore, pressure is going to be given by the equation of state of the given component times the density of that component divided rho c. What is rho e over rho c? Well, that's the density contrast omega. Therefore, this is going to be the summatory of E of W E times omega E. Okay? So you see the effective equation of state is going to be given by a weighted sum of the density contrast of a given species, where the weight is given by its equation of state parameter or function, if it's dynamical. Okay? Therefore, in this picture, we have two ingredients. So we have omega m and Wm and omega m plus W phi omega phi. And what do we do with that? Well, we can express it again as a function of x1 and x2. We just have our omegas up there, we just plug them there. Poof. We have also that. So by doing all the cancellations and put the terms together and so on and so forth, what we get is this expression. This guy is going to tell us if we are in an accelerated phase or not. And you remember, you can recall the fact that we have acceleration if W effective is smaller than minus 1/3, the famous condition that we have for acceleration. Okay? Nice. Then for convenience, I will park the result here. We are going to need that later. We have our first Friedmann equation, the Friedmann equation number 1, which is related to the double derivative of the expansion factor, therefore it is h dot 2 phi dot square plus rho m plus p m. Okay, so we have the contribution of pressure given by by dark energy, and the contribution of pressure given by the matter component. We can plug in here our expression of P with respect to the equation of state parameter. So we're going to use the equation of state for the matter component, given its equation of state. Therefore, we have P dot plus rho m 1 plus W m. And that's what we have. Then again, that's something that we need for convenience later. I'm going to divide this expression with respect to h squared. Okay? If we do that, we just get our h dot over h to the power of 2. So we are just using this expression. We plug in rho m and phi dot with respect to the parameters that we derived earlier. Okay. Therefore, we are going to have, just do the first step because then you see where they pop up, minus k square phi dot square over 2h square minus k square rho m over 2h to the power of 2 1 plus Wm. Okay? This is just a mere substitution. You can see here the first term, the second term, and this Wm comes up from the fact that we change that we expresses the pressure with respect to the equation of state. Okay? Just divide by h to the power of 2. Now what do we have here? H dot to the power of 2. We can express it as a function of x1. And then we have rho m, which is coming from this guy here, right? That's rho m, rho phi with respect to rho phi with respect to rho c. So if I multiply this guy for rho c, I get rho m as a function of x1 and x2. Okay? Therefore, I plug my definition of fig 1, my expression for rho m, into here. And again, simple, very simple trivial algebra, we get minus 3/2, 1 plus Wm plus where am I? x1 squared 1 minus omega phi minus x2 1 plus omega phi. And what is all of that? Surprise, surprise, all of that is the effective equation of state. Confirming the fact that this is the guy giving us acceleration of naught. So you see, double derivative of A, because H is A dot over A, so it contains double derivative with respect to A, can be positive or negative according to this guy here. Okay, just to confirm the fact that this is the one giving acceleration. Therefore, all of these expressions are the way to translate x1 and x2 in something that has a physical meaning. Okay? Nice. Now that we have all of that, keep this in mind. And with this result, we can now start to investigate the basic properties of the phase space. Phase space that now is going to be characterized in terms of x1 and x2, not anymore of phi dot and phi. So we are making this change of variables. So basic structure of the phase space. So x1 and x2. So first basic considerations. Let's give a look. Let's put this one on top. Well, let's give a look when x1 is equal to 0. What's the meaning of it? x1 equal to 0, I recall the definition, it's gone, so that's k phi dot over square root of 6h equal to 0. What does it mean? These are all positive numbers, means phi dot equal to 0. So the axis x1 equal to 0, which means the vertical axis, so let's start to plot it. So we're going to have x1, x2, x1 equal to 0, so this vertical line here is the place where the kinetic term is equal to 0. What is x2 equal to, which is again defined as k square root of v over square root of 3h equal to 0, means potential equal to 0. For all of these lines, R is the site where the kinetic term, where the potential is equal to 0. So that's kinetic, the system is dominated by the kinetic term. Potential is equal to 0. Then we can look, we know that the potential is positive, because otherwise, for example, we could have a fluid with negative energy. We don't want that. Therefore, phi is bound to be equal to 0 or positive. And this tells us, again, looking at x2, tell us that x2, if we look at the definition of x2, so v is equal to 0, it means that, that's equal to 0, and therefore x2 must be as well larger and equal than 2. This is gone. Okay? Therefore we are restricted to this side of the plane, because we want a system with a positive minimum energy, okay, or 0. Then we can look at the constraint that is given by omega m. Again, we have seen earlier it's gone, but it was equal to 1 minus x1 squared minus x2 squared. And what should it be? Can it be negative? A negative density of matter. What's the meaning of it? There's no meaning. Therefore, it could be 0, or could be larger than 0. Again, positive density should be positive, which means that we have a constraint on the physical regime of our phase space. Therefore, x1 squared plus x2 squared must be smaller or equal than 1. Okay, I just bring these two guys and I brought it on the other side. We have a constraint. What does it mean? That's the equation of a circle, right? For a circle of radius unity. So here we have the 0, this is going to be 1, this is going to be 1, and this is going to be 1. Huh? What a nice circle. Therefore, here is unphysical. Our solutions must be restricted there. Okay? Therefore, you understand that this point here, I mean all of the circle, correspond to omega m equal to 1. This region is omega m larger than 0, and this is omega m smaller than 0. Well, actually, sorry, that's 0. Yep.
Why do we want the potential to be positive?
Because, for example, if you think at the dark energy, at the cosmological constant, would be like, you know, your potential would be starting in the middle with V. And V is directly proportional to the density, V, right? So this is density. So rho is equal to 1/2 V dot plus V. Say that you have the cosmological constant, then this guy is static, therefore this is gone, and we have only V. Therefore, V tells you what is the energy density of your fluid, and it should be positive. Okay, if you go to negative, you can build up your theory, okay, but you have instabilities and it's a mess, okay? You're into the ghost regime and it's a mess. Typically, you don't want to go there. Okay, so it's something very fundamental. Good. Then what else? Okay, what happens if we have a solution that tries to escape, for example? Okay? Then we will find out, if we look at the continuity equation, what happened? Okay, don't collapse. So if we look at the continuity equation, where we have our rho dot plus 3h rho, for example for matter, equal to 0, this is going to give us a constraint. Okay, because we would have rho dot is directly proportional to minus rho m. Okay, I just bring this guy on the other side. What happens when rho is equal to 0? So we are positive, we are going this direction. Perhaps is decreasing our, the density of our matter content. We hit this point. Rho is equal to 0. So that's at the border, on the circle. Here. Circle. What happens? The derivative is equal to 0. Rho cannot change anymore. Okay? So you see, there is this physical, this border which has also physical meaning once you look at the continuity equation. Then we can look where we expect to have acceleration. So acceleration, so this will be that's another point. Therefore, where we have h dot dot larger than 0, well, we have to look at the effective equation of state. W effective, which is a function of x1 and x2, as we have seen earlier. Okay, it's up there, you see? Omega effective is a function of x1 and x2. And we have a bound, larger or equal to 0. Therefore, this set a very precise constraint on the region where we expect it. For example, let's keep our life simple, and let's consider Wm equal to 0, matter domination, okay? We have, sorry, matter domination. We have matter is dominant with respect to radiation, okay? Omega m equal to 0. So you get this expression, this one is equal to 0, then you have plus x1 squared minus x2 squared larger than 0. Sorry, smaller than 1/3, okay? Where are we? Yeah, that's omega. Then omega effective, to have the acceleration, must be smaller than minus 1/3. Therefore, once we set omega m, Wm equal to 0, we have the constraint x1 squared minus x2 squared smaller than equal than minus 1/3, right? All the omega m's are left, are gone. We have omega x1 squared minus x2 squared constraint smaller than minus 1/3. This is a line in our phase space. Something like that. Here we have acceleration. Therefore, you immediately know if you have a solution sitting here, we don't have acceleration. We must be on this side. What else do we want? Well, let's give a look, for example, at the cosmological constant. Where would it sit? Therefore, we can get omega phi equal to minus 1, right? This would be, sorry, omega lambda, so just to look where the cosmological constant is. So that's again in terms of x1 squared minus x2 squared over x1 squared plus x2 squared, as we have seen earlier, right? This is generic. When is this guy equal to minus 1? When these two guys are 0. You see, kinetic term, remember x1 is related to the kinetic term. The cosmological constant is not dynamic, therefore these two are equal to 0. And in fact, this gives you always minus 1. x1 equal to 0 is a static field. Is a static field with an equation of state which is the one of the cosmological constant, minus 1. Okay, you see this x1 and x2 are powerful there, just by this very simple consideration of many things are revealing. So this would be our lambda. Okay? Good. Moving on, we have a picture of the key structure of the phase space. So we know that we are confined in a certain regime of x1 and x2, meaning within that half circle. And we see how we can very easily understand, by look where you are on that plane in the solution, basic features of your solutions, basic physical features of your solutions. Now, what we are going to do after the break is to continue our derivation. So we will continue with this study, and we'll start to dig in more and more into the behavior and the structure, further structures that we can have in this phase space. Meaning, we are going to look for critical points. So we are going to look for specific solutions of our system in which x1 and x2 has zero derivative. Okay? These are the maxima and the minima and the saddle point of the solution in this phase space. That will allow us to identify stable, saddle, and unstable points. Okay? And then you will see how, just by finding them, we will know where the solutions are going. Okay? Again, without even solving them. Good. So we can have a break. We can resume at 15 past midday.